Righty-ho. We've been doing this project for about 3 years now, and the original goal of the project was to produce a low-cost digital transmitter board that it's similar to Digilite, but we're using slightly more up-to-date technology. I think it's fair to say that. And we also wanted a board that people could build without having to do a load of SMD construction, because one of the principal market really for this board was to get more digital television activity in the United States, and I don't think they're quite as hot on home construction as we are, but that was what I was told anyway. Also, we wanted to get people involved in new technologies like using field programmable gate arrays, because they are great devices, and they replace an awful lot of TTL in your junk box. So that was another reason. Also, we felt that with all the interest with streaming and high definition video and people doing all sorts of stuff on the internet, we might be able to get some of the sorts of people that were interested in that type of multimedia involved in amateur radio if we produced such a box. And because of that, hopefully we may get some more licensees. But that's just a hope. It may never happen. Anyway, the byproduct of this project is a software-defined transmitter that covers from about 70 megs to 2.4 gigahertz. And will transmit signals up to a bandwidth of 8 megahertz. Right, I think we can have the next slide now, please, Noel.
Done.
You're done? Right, okay. Here are the team members. Art Towsley is the hardware guy. He did the design of the board, and he has been in charge of getting all the manufacturing done and speaking to the board house and the assembly house and all of that. I have done the software, and I'm always looking for people to help me on that. I've done the field programmable gate array software that runs on the board, the C and C++ code that runs on the Linux host, and also the 8051 code that runs on the USB 2 controller chip on the board. Ken is our program manager. He's the guy that does all the Gantt charts and arranges our Skype conferences and what have you, and the publicity, etc. Most of the publicity you've seen in magazines such as DATV and a number of other magazines have been generated by Ken. And Tom Gould is our wizard on printed circuit boards. He's done all the board layouts. So we have to thank him for that, because to me that's the most difficult bit, not being particularly artistic myself. Right, let's have the next slide, please.
Right.
Okay, fine. Right, so as I said, it's very similar to Digilite in that we have to use an external USB capture device for the MPEG encoding, which currently is the Halpage unit. I've recently got hold of I've managed to win an auction on eBay for another hardware encoder made by a completely different company that is supposed to have Linux support. It does both MPEG-2 and MPEG-4, so that could be interesting. We may have a go at that. The trouble is that it's no longer manufactured, but still. Right, the Linux PC does the DVBS encoding, also deals with talking to the Halpage card. We've got it as well as DVBS. We've also got code on there for DVBS2, which is may cause a bit of a problem, because to supply DVBS2 systems you need to get a license from S2 licensing. I've contacted them, but they don't seem to want to reply to my email, so I'm not quite sure what we're going to do about that. Anyway, we also do DVB-T, which I think you heard a bit about yesterday, but that's all done on the PC host, so it requires quite a lot of processing. I'm using a quad-core PC to do all of that. although I have done some experiments with the DVBS on various ARM platforms. So to do the DVBS, you don't need nearly as much processing. On the hardware, we basically do the flow control between the PC and the hardware over USB 2, and we do interpolation of the signal up to the final sample rate, and the filtering, the raised cosine filtering, and also we control the IQ modulator stroke phase lock loop unit. Although I've got 70 to 2400 megs down on the slide, the manufacturer says this device should only work between 72 and 2400. But on the prototype units I've had it going from 65 megahertz to 2.5 gigahertz. So it will work slightly outside of the range the manufacturer has quoted. The lower in frequency, the better it works. The phase noise is much better at the low end than it is at the top end of the band, and various other things are not so good at the top end of the band. But that's just the state of the art as far as the chip is concerned. Now, finally, of course, you'll need to add a RF power amplifier and an antenna. The board produces, at 65 meg, it produces 16 dBm output, and at 2.5 gigs, it produces 14 dBm output. So some amplification and filtering will be required because it's such a wide bandwidth component. There are quite a few harmonics and very clutter coming out at the end of it, so it needs good filtering. Right, next slide, please.
Okay.
Right, the next slide just shows how it fits in an overall system. The DATVExpress board is yellow in the middle, 2 yellows in the middle, and the other blocks just show you the pieces that you need to add to have a complete system. Right, next slide, sorry. You done it?
Sorry. I wasn't paying attention.
Oh, sorry, I didn't speak long enough, obviously.
No. No, it's done. Go.
Right, okay. This shows you what's on the board, basically. We've got, coming in from the PC, we've got a USB controller chip, which is made by Cypress. It's in fact an 8051, and it's got a number of peripheral components on it, like an I2C controller and a serial port on it. It handles the USB interface between itself and the FPGA. We've got Altera Cyclone FPGA. It's quite a small one. We tried to make this as inexpensive as possible, so we didn't go for a large FPGA. And then that controls a dual channel D to A converter. It's a 14-bit D to A converter, and it will clock up to 125 meg samples per second. I haven't had it go at above about 80 meg samples per second because I don't really have a need for it. Then it goes into the analog devices, IQ modulator and phase lock loop. It's a combined modulator and phase lock loop. It also has a 57 dB program attenuator on the out, so that you can change your output signal level to fit whatever you're driving. And we've got a mini circuit MMIC at the end as well. And of course there's all the power supplies, and on the latest board we've added a dual channel ADC converter. It's a very speed one, but we were going to use for things like measuring VSWR, power levels, what have you, so that somebody outside the area, the system will shut itself down, hopefully protect your expensive PA. Right, Noel, I'm going on to the next one.
Go on.
Right, okay. This is the production board. This is the board which we'll be actually selling. We've made a few changes to the previous board. Starting on the bottom left, you'll see some little circles just below the USB controller chip. We brought out the RS232 port, or the UART, I should say, at 5 volts level. That can be used controlling auxiliary equipment. I have some ideas of controlling an upward vertical for 6 centimetres, and until yesterday I was also going to have a 9 centimetre, sorry, a 6 centimetre rather, 9 centimetre. Until yesterday I was also going to have 6Ms, but as that band may look maybe next to useless, I may drop that idea. Now, below the FPGA in the middle, you will see a row of connectors. That is new to the board. We've added this. It uses the low voltage differential output of the FPGA, and that will provide a very high speed serial interface, possibly up to about 600 megabits per second. That will allow the board to use standalone with, say, a much larger FPGA. In fact, you could have multiple, many of these boards connected to a much larger system and just use these boards as RF modulators. So that was something which I'm very keen to play with. Along the top is the power supply. That provides all the different voltages. The FPGA requires, I think it's about 2 or 3 different voltages to operate. So that provides those voltages there. I think the one on the right for analog, the one on the left switching regulator to try and keep the efficiency up. We've had to add some more filtering on the output of the power supply because we were getting the switching frequency of the 5-volt regulator was appearing on the supply to the MMIC, and it was amplitude modulating the signal. So we've got rid of that now. So that means that the little birdies at 1.3 megahertz either side of the carrier appeared now. We've also had to add a lot more copper to the board because the IQ modulator chip draws about 350 milliamps, and it gets very, very hot. You can blame that semiconductor manufacturer. There's nothing much we can do about that. We've also reorganized the analog filter, the anti-alias filter, between the output of the DAC and the IQ modulator to make sure there are no fade mismatches between the two branches, because that's very important in this type of IQ system to keep everything very well balanced and the phase, the amplitude of the two channels the same. Otherwise, if you don't get the phase right, you don't get these unwanted side suppression. And if there's any offset, as explained yesterday on the DATVExpress, you get a carrier that has an IF 0, and you get an unwanted carrier. It's so bad on DVBS, but on something like DVB, it sticks out like as if someone's put a flagpole in the middle of the DVB signal, and it's not very clever. Right, next slide, please, Noel.
Okay.
Right, this is the DVBS output on a Rigol inexpensive spectrum analyzer. This doesn't quite have dynamic range, my HP unit, so it doesn't look quite as good as it really ought to be. The HP, there's much less, there's better skirt selectivity than there is on it. Next slide, please.
Okay.
Right, this is currently what the software looks like. It's very simple. It's just a load of tabs along the across the top. The main one which you see is just gives you an overview of the system, and you can set various parameters for the different modes. We don't implement DVB-T2 yet, or if ever will, because the spec's about 10 times the size of the DVB-T spec, and they do things like rotate the constellation and all sorts of things just purely to try and get rid of this peak to mean problem that occurs with OFDM modulated waveforms. And at the bottom in the little window, I've just added some code, goes and asks the driver what card you've got plugged in. So it tells you, it says to the device, what are you and what driver are you using, what have you. So that, because I've got about 3 different capture cards on my system, and I always pick the wrong one. Okay, next slide, please.
Okay.
Right, as there's been some interest on DVB-T 2 meg bandwidth on 437 on the BATC reflector, I thought I'd show a spectrum of the DATVExpress running DVB-T at 2 meg. I haven't actually tested it because I haven't got a 2 meg receiver, but I have tested the 7 meg version, so I know that I've got all the bits of the process right, but we'll just have to see when I can save up one of those little 2 meg receive dongles, whether it works or not. And I think now we've got the final slide, please.
Okay.
Right, where are we at the moment? Well, the code is nearly ready for your Ubuntu operating system. The still need to make some tweaks to the FPGA code. I've got a serious mock-up in the I2C handler in the FPGA. I've written that myself. It now and again it locks the I2C bus up, so got to find out exactly what's causing that. We're looking for volunteers to help with the software. We have a special software developer program, i.e., if you're going to write software for the device, get the hardware at a considerable price. If anybody wants to know about that program, they can contact via email or via the PM messaging, or just post something on the BATC website. We've got the first batch of boards. They were produced about a week and a half or so ago. We had lots of fun with that. There were some issues. Only one was directed afterwards, and we managed to get one of the, they call it solutions or something, that marks where the edges of the board are in the wrong place, and that gets the guy at the assembly place a bit of a headache. But he rotated the board by 90 degrees. That was okay. Our component supplier managed to wind components on the boards the wrong way around, so those all had to be taken off and put back on. And also they used the wrong type of leader. They used a plastic leader when they used a paper leader on the component, which caused the board a bit of a problem. Oh, sorry, the assembly unit robot a bit of a problem. But that was fixed by basically throwing away those components at the end of the reel. We had a meeting on site a couple of weeks ago. We decided that the price would be $300. That's the price of the United States, and it'll be available at the beginning of January of next year. The reason why we've got 2 months is basically for me to sort the software out and get something which is robust enough that people can use, and we've also to get all distribution files so that you can install it on your machine with to know the ins and outs of Linux. And the UK price, well, we still need to BATC as to how we should be distributing this. I'm hoping the UK price will be very to the US price. Well, I'm hoping it's going to be identical when you convert it into well, it's going to be identical, hopefully, between the 2 places, but it all depends on how we distribute the board. The organisation that we've found formed to produce this board will have a limited life, and it's a non-profit operation. So at the end of the life of the organisation, any money that's additional money will be donated to worthy amateur radio causes. Each of the members of the team will decide where their share of the spoils will go. While the project's running, any money that any profits that are made will be put back into improving, reducing the price, and possibly producing other modules or other things for the digital ATV. Right.